Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue looking at deformation and metamorphic rocks. So in this video we're going to be thinking about what processes will be occurring at extensional and strike slip settings, and these are going to correspond to divergent and transform plate boundaries, and this is going to correspond to section 8.10 of your textbook. So we're going to begin with divergent plate boundaries. What kind of things are we going to see going on in these areas? Well, we know that divergent plate boundaries represent areas of the Earth's surface that are undergoing active extension. So we have tension going on. So we can see that in this instance we have one block of rock over here on the left that wants to go this way, one block of rock over here on the right that wants to go this way, and that means that this area in the middle is finding itself being stretched, it's being extended. Now we know that this extension is going to lead to the formation of fractures, so the rock's going to break, and these fractures are going to have pieces of rock which will move relative to each other, and these pieces of rock are going to drop down relative to each other. So this means we're going to have the formation of normal faults associated with the divergent plate boundary. So all of these here are going to be normal faults. We're going to have blocks of rock dropping down relative to the adjacent block of rock. Now, we know by now that obviously underneath our divergent plate boundary we're going to have decompression melting of the mantle, and this is obviously going to create magma which is going to start rising through the crust. So obviously as this magma starts to rise through the crust, what is it going to do with regards to metamorphism? Well, obviously we're going to have a lot of contact metamorphism taking place because the heat from this magma is going to be baking the surrounding rock. We're not really going to have regional metamorphism taking place because we're not really thickening the crust. In fact, we're thinning it. And in the case of subduction metamorphism, we're not going to get that at all because there's just no subduction going on. So all of the metamorphism we're going to get at this continental divergent plate boundary is going to be almost exclusively related to contact metamorphism. Now, where we have an oceanic divergent plate boundary, we have a similar situation. So we have one block of rock that wants to go this way, one block of rock wants to go this way, and once again the rock that's in the middle between these two blocks finds itself being stretched, it's being extended. And so just like our continental divergent plate boundary, we end up forming lots of normal faults. So once again, normal faults form where we have extension, so the crust is being stretched. Now, once again, the mantle underneath our piece of thinning crust will begin to melt through decompression melting, and this is going to lead to the formation of magma. So what type of metamorphism are we going to see associated with oceanic divergent plate boundaries? Well, in the case of the oceanic divergent plate boundary, we have a mafic magma which is moving through mafic igneous rocks. In the case of the continental Rift Valley here, we're going to have mafic magmas moving through rocks which are of felsic to intermediate composition. So the magma is going to be hotter than the rock, and so it's going to bake it. We're going to see metamorphism occurring. In the case of oceanic crust, you have a magma which is moving through rock which is made from the same magma. So essentially your basalt is being put in contact with a mafic lava, mafic magma, and it's not really going to cause that much change because, you know, the basalt is capable of surviving the temperatures to which it is being exposed. So not much is really going to happen. Now, the metamorphism that we do find at divergent oceanic plate boundaries is primarily the result of circulating water. So as the water circulates around, it will do what we refer to as scavenge. So as the water moves through the oceanic crust, it will steal elements as it goes. You know, so it might grab some calcium, it might grab some sodium, it might grab some silicon, it might grab some, I don't know, nickel as it's moving through the crust. And so it will dissolve these elements into this circulating water. And so as this water moves through the crust, eventually the water will interact with a rock and there will be a chemical reaction that takes place. And so the chemical makeup of our hydrothermal fluid, our hot water, and its reaction with the oceanic crust is going to lead to the formation of new minerals, and these new minerals will be referred to as metamorphic hydrothermal minerals. So once again, in the case of a continental divergent plate boundary, most of the metamorphism is going to be the result of contact metamorphism, because you're putting very hot magma in contact with rock which formed at a lower temperature. In comparison, at a divergent oceanic plate boundary, you are putting very hot magma in contact with rocks which can take those temperatures, and the minerals which make up the basalt are perfectly happy at those high temperatures, so there's not really going to be any contact metamorphism taking place. Instead, the metamorphism that we do see at oceanic divergent boundaries is going to be related to fluid circulation. So we're going to get the formation of hydrothermal minerals related to metamorphism. Now, as we've discussed, in both the continental divergent plate boundary and the oceanic divergent plate boundary, the extension, the tensional force, is going to be accommodated through the formation of normal faults. And we can see that here on this diagram. So we can see right here are blocks of rock, and we can see that this block of rock here is dropping down relative to this block of rock right here. And so this is going to represent our normal fault. Now, the one thing I will point out is on this diagram here, you can see that it does actually show contact metamorphism as occurring, but in reality, I'm just going to say this one more time, the amount of contact metamorphism that we see occurring at divergent oceanic boundaries is very, very small. This diagram really overemphasizes it a lot. It makes it seem like there's more of it going on than there really is. The vast majority of the metamorphism will find that these oceanic divergent boundaries is going to be hydrothermal. So what type of deformation and metamorphism will we see associated with strike-slip faults? So once again, where we have a strike-slip fault, we have a block of rock which is essentially trying to move in two different directions. So obviously in this case, the left-hand side of the block is trying to move in this direction, and the right-hand side of the block is trying to move in this direction. And that means we have a build-up of stresses in the center of our block, located about here. So if our block fails in a brittle fashion, obviously it will break into two, and so this block will move that way and this block will move that way, and so all of the deformation is going to be limited to this fault plane right here. So where do we see these types of strike-slip faults forming? Well, they tend to be associated with transform plate boundaries. So think of areas like the San Andreas fault is the definitive, the classic example of a strike-slip fault. But of course, we also know by now that we have these transform faults associated with mid-ocean ridges. So in this case, we have the mid-ocean ridge in the South Atlantic, and you can see that these sections of the ridge which run approximately north-south, those are the divergent sections where new crust is being made, but we know that these divergent sections are joined together by these transform faults, and so these transform faults are accommodating movement in this fashion. The blocks of rock aren't going up or down relative to each other, it's just allowing these pieces of C4 to slide past one another. So we can get a sense of the movement on our strike-slip fault. So this is actually an image, or a radar image for the San Andreas fault. And what we can see is, you can see we have a river channel coming down here, and we can actually see the fault plane right there. And we can see that as the river comes down, it hits the fault plane, it takes a sharp right turn, moves along the fault plane, takes another sharp right turn, and then flows downwards. Now, once upon a time, this river channel was actually located about here. But because of the strike-slip fault movement, the river, of this side of the fault, this portion of the river has slowly been pushed to the west. And so this gives us some idea about the fault movement. Now, in terms of metamorphism associated with strike-slip faults and shear zones, there is no real metamorphism that's going to take place. The deformation may well lead to the formation of rocks which have fabric, so they may have foliations or lineations to them. But in terms of metamorphism that's going to actually create new minerals, well, that doesn't really happen at strike-slip faults, because you don't really have any heat, so there's no magma being generated, and so that means that contact metamorphism isn't going to occur. But we're also not going to get regional metamorphism occurring because we're not building up or increasing the thickness of the crust. All that's happening is we've got two pieces of rock moving relative to each other. So this means that strike-slip faults are commonly not associated with large amounts of metamorphism. Any metamorphic rocks that you do get associated with a strike-slip fault will be the result of deformation which is occurring along the fault plane. So they're going to be very, very limited in their occurrence. Alright, thank you for watching everybody and have a good day.